Hello, my name is Jakub Michalik, and together with Kamil Nowak, we would like to present the results of our analysis of the effect of artificial patina on the legibility of marks on objects. When examining artifacts made of bronze, it is very common to see their different states of preservation. Most often their states of preservation was influenced by the place where they were deposited in the ground, but also by conservation methods of subsequent storage in a warehouse on museum exhibition. Traceological analysis can be carried out on bronze artifacts in various stages of preservation, but we have to reckon with the observation of traces that did not originate in the former times and may have been the results of archaeological and conservation work carried out. On the other hand, one should consider whether traces on metal objects could be covered by a layer of patina so thick that they become illegible. Every archaeologist, museologist, and conservator dealing with metal objects has come into contact with metal corrosion. Corrosion looks different for each type of metal or alloy, but we will only focus on the corrosion of copper tin alloy bronze. To begin with, we need to distinguish between two main types of corrosion. A completely harmless sign of corrosion of copper and its alloys is the formation of malachite-colored deposits known as noble patina. Noble patina is formed by well-bonded alkaline copper carbonates and sulfates. As the name suggests, noble patina is desirable product. More importantly, such a layer is harmless to the substrate metal and even protects from further corrosion. The second group consists of chlorine-copper compounds. It is from this that bronze disease originated. Initially, in the presence of chlorine ions, grain-brown copper and chloride is formed. When exposed to moisture and oxygen, which must come from the air and copper oxide, cuprate chloride is formed. It is highly soluble in water and decomposes into cupric oxide and hydrochloric acid. The hydrochloric acid in turn attacks the metal copper. Copper chloride is formed again and the whole cycle repeats itself. As a result, a small amount of chloride causes a corrosion process known as the disease of bronze, which is dangerous in its consequences. Then, in a worst-case situation, conservators are forced to remove the entire corrosion layer to preserve the artifact, and a popular method of preservation of bronze objects is to carry out a process of artificial patination again. For our experiment, we used a replica knife cast by traditional methods from certified bronze, so we knew the extract proportions of the alloys used and thus has good comparative material, so we did not have to carry out a test on the original relics from fear of damaging them. On the knife replica we made scratches resembling of machining and grinding marks that can be observed on artifacts. We used the microscope photographs taken as a model to compare the visibility on the marks with each other when carrying out the artificial patination process. One wonders whether the artificial patina may affect the obliteration or formation of new marks on objects, which may hinder traceological investigations. For the experiment, we was dedicated to apply an artificial patina using acetic acid and carbon dioxide. The choice of this method was dictated by the ease of execution and small number of ingredients required. The method involves placing calcium carbonate with acetic acid at the bottom of the desiccator and a bronze object moistened with an aqueous solution of acetic acid on the top. The combination of calcium carbonate with acetic acid produces large amounts of carbon dioxide, resulting in the formation of basic copper carbonate and copper acetate on the copper surface. The process takes several days for the compounds to form, but every so often the metal objects need to be cleaned and the mixture removed at the bottom of the vessel. The process should be carried out under laboratory conditions, as there is a high risk of accidental contamination of the object with chlorides, nitrates and sulfides, resulting in corrosion faulty. After the first few days, we could see a thin layer of patina and the knife began to take on a green color. At that time, the marks we had made were still visible, although the shallower ones were already beginning to fade. After about a month, the patination process was complete. The result of the work was a rather thick layer of patina that covered most of the marks we had made, and only the deepest ones were barely visible. Finally, we decided to still sand the resulting layer of artificial patina to capture additional marks, and also some sections the patina was peeled off to visually determine its thickness and capture the sanding marks. As a result, by making microscopic observation of the knife at different stages of artificial patination, we obtained different results. With a thin layer of artificial patina, the traces were still visible, but later they disappeared completely and were only visible when the artificial patina was removed. This shows that the application of artificial patina can interfere with traceological observation, which are most often possible, for example, with artifacts with original patina. However, the analysis is only a contribution for further analysis, including, among other things, measuring the thickness of the patina, comparing the chemical and physical properties of artificial and noble patinas with each other, and as well as carrying out research on other artificial patinas, including those that are available as ready-to-use conservation preparations. Thank you very much for your attention. We hope to be able to share our further research results with you in the near future.